Physical reality is the output of an active, continuous computation. Beneath the surface of matter, a substrate of data is constantly writing itself into existence. Standard physics struggles to explain two things: the mechanical origin of the arrow of time and where the universe stores the historical data of every past event. These problems find a solution if the universe operates as a directed acyclic graph, or DAG. A DAG is a computational structure where data moves in one direction through a series of nodes, with no possible way to loop back to a previous state. Each new entry in this ledger physically constructs the next moment of existence. Time is the structural growth of this data. To see how this architecture begins, we have to look at the simulation's simplest variables before they are allowed to interact. These are topics. At this stage, they are isolated nodes, variables that have been defined but not yet assigned a history or physical position. Because these topics have no prior entries on the ledger, they possess zero mass and no measurable impact on the surrounding field. For a topic to gain physical reality, it must be forced into a collision. Existence only emerges when isolated nodes begin to negotiate their shared states. The simulation targets specific nodes, preparing them for an interaction. Before a collision happens, quantum rotation gates assign mathematical stakes to each topic. This value defines the level of influence the node will hold over the final outcome. We quantify this using a Shapley value. In game theory, a Shapley value calculates the exact marginal contribution of a single player in a cooperative game. Here, it dictates the precise leverage a topic brings to a physical event. A particle's impact is determined by its computational weight before the physical collision ever takes place. As these topics smash together, they enter a negotiation called the debate. Their competing contexts and Shapley values grind against each other inside a quantum logic gate. This is the moment of consensus. It is the transition from a probability to a definite state, the wave function collapse. Making this decision requires a physical price: the generation of heat, or entropy. This finalized consensus locks into place, creating a permanent node that bridges the original topics. Across the universe, millions of these collisions interlock to form a 2D holographic ledger. Because this graph is append only, every new node creates an irreversible sequence. It is impossible to unwrite a consensus. This structural irreversibility is the mechanical origin of time's arrow. Every physical interaction etches an immutable block of data into the architecture of the universe. We can test this by comparing two seemingly identical particles side by side. We compare the raw 4, a particle injected into the simulation with no past, against the iterated 4, which was forged through the ledger's history. To see the difference, we measure their von Neumann entropy. This metric quantifies the hidden information and entanglement stored within a quantum state. This chart shows the raw 4 as a single probability bar. Its zero entropy proves it has no connection to the past. The iterated 4 shows a wide distribution of probabilities, carrying the computational scars of every prior collision. This is a city plot of the iterated particle's density matrix, a three-dimensional map of its quantum states. These towering red and blue bars represent the entanglement between the particle and the ledger. This is causal memory. An authentic particle is mathematically linked to the history of the entire system. When we pull back from this data cityscape, the microscopic complexity scales up into the cosmic structures we see in the night sky. Because the ledger only appends data, the universe is physically capable of throwing information away. Every movement and every choice is recorded in the heat of entropy. Reality is a mathematically closed, eternal memory drive. No information is ever lost.